So we've looked at voxels containing either a vector or a scalar value. And we shortly crossed that, but how do you encode a geometry into a volume? And that's where signed distance fields come in. What is a signed distance field? Let's just look at one slice out of our volume. Assume we have some geometry going through that slice of the volume, which is this curve. This is the surface of our geometry that we'd like to encode into the volume. And the way this is being done is we take the centers of our voxels, those are the dots in here, and for each of those voxel centers we calculate the distance to the surface. And you can actually think of this as the radius of a circle around the voxel center that is touching the surface here. So these are all those distances for the interior voxels visualized. Now we also do that for the voxels which are outside of a geometry. The way we encode what's inside, what's outside is the inside gets a negative prefix, the outside gets a positive prefix, which is also called a sign. Voxel values inside our geometry have a negative sign and outside of our geometry have a positive sign. And what we do is we store those values into our voxels, just those distances towards the surface. Now you can guess why it's called a signed distance field, because it has a sign, negative or positive, and it stores the distance to our geometry in a scalar field, that is a bunch of voxels. Let's quickly go over how to create an SDF in Houdini with standard volumes. Let's drop down a test geo. And the easiest way to convert a geometry into an SDF is the ISO offset node, which we're just going to wire up here, highlight it, and by default it's set up to turn this geometry into a fog volume, which is not what we want, but we want an SDF volume, a signed distance field, and we want its resolution to be a bit higher than this, so let's set it up to be voxels by size and dial down the voxel size to something like this, and we see we have now an SDF that is a signed distance field, a volumetric representation of our geometry. And why is this so cool? Some of you might have watched one of the early Entagma tutorials, and what we did there is we actually applied a blur to it. So what you can do is, like in image processing on pixel basis, you can have certain filters work through your volume. For example, a blur. Let's demonstrate by dropping down a volume blur here. Make sure to check use voxel radius and wire it up, highlight it, and let's increase the number of blurring passes. And what you can see here is I can blur out my geometry as I like, or I could do Boolean operations really easily, just like multiplying or subtracting like I would do in Photoshop with a layer. And I could do that here as well. I would not get into trouble because of mesh flow edges or points, because all the data is stored into voxels, so I'm basically doing the same operations as I would in Photoshop on pixels. This is extremely powerful. Let's highlight the ISO offset again, and this representation is a bit coarse, so let's decrease the voxel size to increase the resolution, so dial down the voxel to a third of its size. And what I'm noticing now is this takes an awful lot of time to calculate. So converting my standard test geometry to this volume, which is okay detail-wise but not amazing, already took some seconds, and I can see those weird thingies here, and what are they? So let's drop down a volume slice here. Have a look at this. Set the volume slice to be in the YZ plane, and we can see this. This is weird. Let's offset through the geometry, and here as well. I can see those kind of errors peeking through here. So using ISO offset and standard Houdini volumes to generate an SDF, on the one hand is kind of slow, and on the other hand is not really error proof. So what can we do about this? Well, we can actually use VDBs.